We will continue working with quadratics in Topic 2B. In this topic, we'll solve quadratics. Lesson 2.4, Complex Numbers. We'll solve quadratics using square roots. We'll add and subtract with complex numbers. We'll multiply and divide with complex numbers. And we'll solve quadratic equations with complex solutions. We're going to first start with example 1a. How can you use square roots to solve each equation? In the first example, we have x squared equals 16. The opposite of squaring a number would be to take its square root. If you square root the left side, you must square root the right-hand side. That cancels out the squared on the left, and we have just x equals. But when you solve a quadratic, there are two solutions because of the axis of symmetry. What that means is we need to put a plus and a minus out in front. The square root of 16 is a perfect square, and we get 4. This means on the coordinate system, we would have an answer at positive 4, 0 and negative 4, 0. Let's try the example on the right. Same idea. We have x squared equals negative 9. To get x by itself, we would take the square root of each side. It cancels out with the squared. But now we've got plus or minus square root of negative 9. Because of the negative on the inside, that means we have no real solution. And there are no x-intercepts for the graph. In order for us to try to simplify a square root, we introduce the imaginary unit I. It literally represents an imaginary solution. The definition for I equals the square root of negative 1. An imaginary number, then, is any number that has an I associated with it. And this imaginary number is useful in helping us simplify square roots. To work with numbers involving I, we look at what's called a complex number. And a complex number in standard form is written a plus bi. So it has a component of a real part, which is the a part, and an imaginary part, which is that bi part. When simplified, when you are simplifying, you might be asked to write your answer in standard form. Let's see how that works with these examples on the right. Simplify each expression. Write your answer as a complex number in standard form. Based on those directions, we have to have the model a plus bi when we're done. In our first example, we have the square root of negative 49. If it's already a square root, we don't have to put plus or minus out in front. But the first thing we'll do is we'll factor out that negative with an I. And you literally just put it out in front of the square root, and it eliminates the negative from the inside. So the inside now, we just have the square root of 49. Now simplify, if possible. 49 is a perfect square, so we can simplify that. The square root of 49 is 7. 7 times I on the outside would just be 7i. Now that's the imaginary part, but as a complex number in standard form, we need the a part out in front. Since this is all we have, technically there isn't an a term. That means it defaults to 0 as a placeholder. 0 plus 7i is how you'd write your answer in standard form. Let's try another one. The square root of negative 7. Again, the first thing you'll do if you have a negative on the inside is factor that negative out by using I, and then you make the inside just positive, so positive 7. This one doesn't simplify, so we leave it as I times the square root of 7. But to put it in standard form, again, our a value is 0, so we'll write it 0 plus I square root 7. That is our complex solution to that negative radical. Let's try the last one. I've made a small adjustment to this one. We have the square root of negative 50 plus the square root of positive 121. The first thing you'd want to do if you have a negative inside the radical is factor that negative out simply by putting I in front. And then we have positive 60 on the inside. Or 50, sorry, 50. And then the square root of 121, make sure you keep that positive. I changed it from the notes template. That's actually a perfect square. The square root of 121 is 11. So now we're done with that part. But that 50 on the inside of the square root, it isn't a perfect square, but it has a perfect square factor. 25 goes into 50 2 times, and 25 is a perfect square. That means we can take that out of the radical. The square root of 25 is 5. And we already have that I out in front. That would be 5 times I. I'm going to rewrite that 5 though. So that would be 5 times I, and that 5 cancels out the 25 on the inside. We still have that 2 on the inside. That doesn't go away. And then we're going to add 11. This is a pretty big imaginary part of our term. The 11 is the A part of our term. So this is in the wrong order. To write it in standard form, the A part would have to go first. We're just going to flip this around. 11 plus 5i times radical 2. And that's your number written as a complex number in standard form. When you don't have to evaluate a square root and you're just given a complex number, you can easily find the sum and difference by combining like terms. Here's how that works. If you have the complex number 4 minus 7i, and you add negative 11 plus 9i to that, we will simply combine the a's as our like terms, and then we'll combine our bi's as the other part of our like terms. 4 plus negative 11 would be negative 7. That takes care of that part. Negative 7i plus 9i is positive 2i. That takes care of that second part. And that's it. When you add, you're simply combining like terms. To subtract, you do the same thing. So in the second part, it says, what is the difference? The key with subtracting, though, is make sure you subtract both parts, the A and the BI part. So I like to distribute that negative in, and then that eliminates the parentheses. The negative to the 2 just makes that minus 2. But notice if you subtract negative 5i, that would actually make that positive 5i. Once you eliminate that parenthesis part with the subtraction, it's combining the a's and b's again. Now the a parts, we have a 6 minus 2. That would give us a difference of 4. For the b part, if we have that 8i minus negative 5i, that changes to plus, and we'd have plus 13i. And there's your difference in complex form, or as a complex number in standard form. When you're asked to multiply complex numbers, you're either going to distribute or FOIL. Once you get rid of the parentheses, you'll combine like terms. When you FOIL, you're really treating I like a variable. If you ever end up with I squared, you can substitute negative 1 in its place. Let's try the 4 examples on the right. In that first example, we have 2i out in front. And we want to multiply that into the 8 minus 9i. So we will distribute into both terms. 2i times 8 would just be 16i. So we treat I like a variable and we multiply our constants together. Minus 2i times 9i, well 2 times 9 is 18, and I times I would be I squared. Now if we have I and I squared, those are technically not like terms. But we said I squared equaled negative 1, so then this would become 16 minus 18 times that negative 1. And 18 times negative 1, that would give us 16 minus negative 18. 16i minus negative 18. And that double negative would make that positive. To write that then in standard form for a complex number, we'd put the 18 first, and then we'd add 16i. That would be your solution in standard form. On the right, we have 2 parentheses, so we're going to FOIL. First, outside, inside, last. I'm going to take the 3 in the first parenthesis and multiply it to both terms in the second parenthesis. 3 times 3 is 9, and 3 times positive 2i, 3 times 2 is 6, so it'll be 6i. I'm then going to take negative 2i times 3 and negative 2i times positive 2i. Negative 2i times 3 would be negative 6i, and negative 2i times positive 2i would be negative 4 times I squared. Now, if I were to combine like terms, the positive 6i and the negative 6i in the middle cancel out. That leaves us with 9 minus 4 times negative 1, which would be negative 4. So then it's 9 minus negative 4. Well, we're going to get a double negative there. That cancels out to be positive, and we end up with 13. But in standard form, we have to have the a plus bi model, so then that converts to 13 plus 0i. All right, you try the next one. Pause the video and see if you can FOIL and combine like terms. Once you think you have it, let's see how you did. Did you get 24 minus 18i? I hope so. When I FOILed, I took 6 times 2 and 6 times negative 4i, then 3i times 2 and 3i times negative 4i. And I got 24 minus 18i written as a complex number in standard form. All right, please try that last one. Pause the video and FOIL them together. Then combine like terms and press play when you're done. All right, let's see how you did. I took negative 2 times negative 3 and got positive 6. Negative 2 times 12i and I got negative 24i. Then I took negative 9i times negative 3 and that gave me positive 27i. Negative 9i plus 12i would be negative 108i squared. I combined like terms and simplified my I squared to negative 1, and I ended up with 114 plus 3i. The last thing we'll talk about in the video are complex conjugates. If a plus bi is a given complex number, then its conjugate is a minus bi. We literally just change the sign on the inside for that complex number. And this is pretty easy to do. Example 4, what is the conjugate of each complex number? In our first complex number, we have 4 plus 5i. To make the conjugate, we're just going to change the sign on the inside to 4 minus 5i. And that's all it is. Although let's make sure we can tell the difference between, there we go. That's all it is. In that second example, we have negative 3 plus 2i, and again, we're just changing the sign on the inside. And that will give us negative 3 plus 2i. That's your complex conjugate. For that last number, we're in bi form, but we want to put it in a plus bi form. Technically, our a value would be 0. So that would be 0 plus 6i, since the 6i was positive. To change the sign in the middle, that would simply become 0 minus 6i. And there's your complex conjugate. We'll use these complex conjugates in division. This is it for the video today. Tomorrow in our Google Meet, we'll complete our notes for 2.4.